So in the last class, we were talking about generic methods. So just to quickly remind you what's going on here, you can create a method, you can create a class that's generic, you can make an interface that's generic, you can make a method that is generic. You can combine all of them together. So you can have a class that's generic that implements a generic interface that has generic methods. So to introduce generic methods, I'm going to do them in isolation because throwing everything together makes things a bit complicated. So here we have a utility class called queues. Queues operates on our queue classes that we've implemented in the course. We have one generic method so far. We have a method called clear. So it takes in a queue. And now remember, queues are generic. So normally you would say something like queue and then the angled brackets, and then you would put a type in here. So here we've got our placeholder for our type T. Now, as soon as you do that in a non-generic class, you have to make the method generic. Right? So now the method is also generic. This simply says that this method is using a type, it has a generic type T, which is being used over here. Right? And so to clear a queue, it's simple, right? You just call dequeue until the queue is empty. If you look inside the method, though, you'll notice that something funny is happening. The method's generic, but the type T is never used inside the method. So there is a way to change the notation that's here so that you don't have to make the method, you don't have to mark the method as being generic in some type T. I don't think we'll actually get there in this course, though. So we need like another week or so to get there. And I think we're going to run out of time before I show you how to do that. So for now, if the fact that the method is not using T anywhere inside of it bothers you, that's good. It probably should, right? But you can simply ignore it for now. If you want to skip ahead in the lecture slides, the second last set of lecture slides explains what to do in this case. This is perfectly fine, so it's perfectly legal. It just looks funny when you look at the source code. Okay, so let's add another generic method. So here we've got a method called enqueueAll. Right? So it takes the elements from the source collection, adds them to the destination queue. Right? Now here, the element type, or sorry, the generic type does show up inside the method body. So this one makes a little bit more sense. Right? Our collection is generic, so it's a collection of some element type T. Right? We have a queue of some element type also T. So here they have to match. So when someone calls this method, they have to use a collection of, say, string. They also have to pass in a queue of type string, where the element type is also string. And again, so you mark the method as being generic. Implementing the method is easy. Right? You simply iterate over the source collection and enqueue the element to the destination queue. dequeueAll is similar. You've got a source queue, you've got a destination collection. You would like to empty the source queue, adding everything to the destination collection. Right, so it's very similar to the previous method. Right, if you have a queue of string, you also need a matching collection of string. Right, if I want to take strings out of a queue, it makes sense that I'm going to put them into a collection of string. Has anybody picked up on about what I just said there? I think I might have asked this question in the last lecture too. It's a bit funny. Anybody? Right. So if I have a queue of string, right, and I have a list of string, it makes sense that I can put the strings from the queue into the list. Right. But something else also makes sense. Right. So if I have a queue of strings, right, I ought to be able to put that into a list of object as well, right? Because a list of object can hold anything. Right. And so the fact that these types here match exactly is a little bit restrictive when you think about inheritance. Right? Again, there is a way to work around this. So the Java's generic system does let you specify your types in a way where inheritance still works. Again, if you want to know about that sort of stuff, so if you're curious how that works, skip ahead to the second last set of slides. I'm not 100% sure that we're going to get there in this term. Okay, finally, the last method is contains. So I'd like to search a queue for some object. If I find an element that's equal to obj, I would like to return true. If I don't find an element equal to obj in the queue, I'd like to return false. Furthermore, I would like to not permanently modify the queue because anybody who's calling this method probably doesn't want you to permanently modify their queue. Right? Okay, so remember when we did this with a stack, we needed to make a temporary stack. So we took all the elements out of our original stack, put them in the temporary stack, and then reverse the process. You don't have to do that with a queue because of the way that a queue works, right? If I take the first element out of the queue, look at it to see if it's equal to the object I'm looking for, I can just stick it back in at the end of the queue, right? If I repeat that process for all the elements in the queue, your queue is restored back to its original state, and you search the entire queue. And so for a queue, it's a little bit easier. You just write a loop that runs a number of times equal to the size of the queue. You simply dequeue the queue and then check, is the element that you dequeued, is it equal to obj? Right? If it is, then you know the result is true. Right? Now, you don't want to return true at this point. Right? You don't return true here because you've changed the queue in this step up here. So you need to enqueue the element back into the queue, and you need to make sure you do repeat this process n times, where n is the number of elements in the queue. Right? That restores the state of the original queue, and it lets you search all the elements in the queue. Right? When you're done, you can finally return the result, whether it's true or false. Okay, so that's an introduction to generic methods. There is a little bit more to say about generic methods. Again, skip ahead to the second last set of slides if you're interested in what else you can do with these things. Right? But I'm not 100% sure we're going to get there in this course. Okay, we're going to look at one more. We're going to look at the implementation of a few more data structures. So now we're going to look at lists. The plan for next week is to look at sets and hopefully maps. So I'm going to go back to one of the lectures, two of the lectures that we missed, tell you about sets and maps, and then hopefully I'll show you how to implement them in a bad way, right? In an inefficient way. It's not bad. We're going to show you the inefficient implementation. If you take the data structures course, you'll learn how to implement them efficiently. Okay, so what's a list? Well, we all know what a list is, right? So a list is just a sequence of elements, and they're numbered. Right? You're allowed to access any element of the sequence using an index. Right? And we've used ArrayList in this course a fair bit, and so you should know how lists work. Even though you know how they work, it's useful to look at how you actually implement one to understand why certain operations with ArrayList are efficient and why other operations are inefficient. Okay, so we've learned about interfaces, we've learned about generics. We might as well put everything together and make a generic list from the get-go. We could use Java's list interface, but it's pretty big. It's not that big. I mean, it's not that big. It's too big for a lecture. Right? So if I want to implement, I'm going to implement a simplified version of Java's list interface. Right? So we're going to provide the following methods here. Size is easy, isEmpty is easy. Right? Get and set an element from the list. Those are also easy to do. It's the last four, which are more complicated. Right. So adding an element to an array-based list, sorry, adding an element to any kind of list, you have to pay attention to some details. Right. Inserting an element into a list, you have to pay attention to more details. Removing an element from a list is like adding an element or inserting an element into the list. There's a bunch of stuff you have to take care of. And providing an iterator for a list also has a bunch of details that you need to take care of. So the first few methods, easy to implement. The last four methods, slightly harder. So our interface simply looks like this. So I'm calling it slist for simplified list because it's not Java's full list interface. We want an iterator. And so we're going to have to also extend the iterable interface. So here's your first example of an interface that extends another interface. So just like a class can extend another class, an interface is allowed to extend another interface. Right? All this says is that an slist is also an iterable. Right? All that means is that every slist has an iterator method. Right? So iterator is the method that comes from iterable. Okay, so how do you implement this thing? Well, it basically looks a lot like a stack. So if you want to make an array-based list, you can start with the implementation of an array-based stack. And so inserting an element into the list, so for example, adding an element to a list is like pushing an element onto a stack. It works the exact same way if you're implementing it with an array. Right? If you want to remove an element from the back of the list, that's exactly like plopping an element off the stack. The methods that require some extra explanation are when you have to do something in the middle of the list, right? Middle or the front, right? It's all the same thing. Okay, so I'd like to insert into the middle of this list. So the squares shaded in blue, those are existing elements in the list. So elements 0 through 8, there's something in the list. Elements 9 through 15, there are no elements in the list. Remember, there are elements in the array, though, right? All the array elements here are null or have some reference in them. They're just not part of the list. Okay, I would like to insert at index 4. So what that means is you need to make a hole at this location so that I can insert the new element. So what do you have to do? You have to take all of the elements 4 through 8, right? And I need to move them one position to the right. That creates a free space here where I can insert the new element. Right? So it looks like if you're going to insert into the middle of the list, right, you're going to have to shift elements over one position to the right. Okay, now how do you shift the elements one position to the right? Right? So it seems like a relatively straightforward problem. Right? I want to take the element at index 4 and move it to 5. I'd like to take the element at index 5, oops, sorry, move it to 6, right? And so on and so on and so on. Right? You don't want to do it in that order. If you move the 4, the element index 4 to the position at index 5, right? You end up overwriting the element at index 5. Right? So when you do this procedure, you have to start at the end, right? Move 8 over one position, then move 7 over one position, and then move 6 over one position, so on and so on and so forth. Right? So if you're going to shift to the right, start at the end. If you're going to shift to the left, start at the beginning. Right? So when we remove an element, we're going to shift left. So you'll start at the beginning of the, I guess, the subsequence and move everything one position to the left. Okay. The funny thing about that insert method, well, there's two funny things. Funny thing number one, it's called add, which is weird. Funny thing number two is that in Java, the Java standard library implementation of a list lets you add or insert at the index that's one past the end of the last element. Right. So in other words, you're allowed to insert at the position equal to the size of the list. Right. 10 elements in this list, you're allowed to insert at index 10. Right. Even though index 10 is not a valid index for the list. So that's a little bit unusual. If you want to add at the end of the list, though, you don't actually have to write any code. Right. You can just call our existing add method, which already adds at the end of the list. So it turns out we don't have to do anything special here. We can just call the other version of add. If you want to remove an element from a list, so I'd like to remove the 4, you don't really remove the elements, right? All you end up doing is you just take elements 5 through 10, right? And shift them one position to the left. You don't actually have to do anything with this element here. Well, you might want to return it back to the caller, but you don't have to write any special value into here. Right? You just start copying element 5, copy it over into element 4, right? Take 6, copy it into 5, take 7, copy it into 6, and so on and so on and so forth. Right? And when you're done with that operation, all of the remaining elements have moved over one position to the left. Oh, sorry. Okay, so this doesn't look too bad to implement. Let's see what it looks like in code. This is not. Oh. Sorry. What is going on here? There we go. Okay, so if you actually pay attention to those drawings that I just showed you, it should be obvious that when you insert or remove an element into an array-based list, right, the worst case complexity is in ON. Why is it in ON? Because you might have to move up to n minus 1 elements. Right? If you remove the first element of the list, you have to shift all of the other n-1 elements one position to the left. Right? If you add at the front of the list, you have to shift all of the n elements one position to the right. And so if you're using an array-based list and you need to insert or remove, not at the end of the list, but somewhere else, you might want to reconsider whether you should be using an array-based list. Right? The operation is slow for a list. Right? Okay, how do you implement this thing? It looks exactly like a stack. Right? Instead of keeping track of the top element, you just keep track of the number of elements in the array. Right? So that's size. It's a generic list, so we need an array of big O object to hold our elements. Right? Remember, we can't make an array of type E, even though we'd like to. Right? Java doesn't let you do that, so we need an array of big O object instead. Default capacity is just the size of the list that's made by the no argument constructor. So the no argument constructor makes an empty list. Right? Now remember, when you make a list, you still have to make this array, right? So even though there's nothing in the list, you still have to initialize the array. Right? Remember, you have a variable here called ARR. Right? Remember that all that is a reference to an array. It doesn't refer to an array yet. Right? The constructor must make a new array. So we make our new array of object, size 16, and we set the size of the list to 0. Size is easy. You just return that field there. Add is exactly like push for a stack. Right? The first question you ask is, is there room in the array for the new element? Right? So is the size of the list equal to the length of the array? Right? If it is, you need to make a bigger array. How do you do that? Use arrays copy of. Right? So copy your current array, right? Multiply the size of the array by 2, right? And reassign the new array back to this .arr. Right? So that makes you a array that's twice the size as your original, has all of your original elements in it. Right? Once you've got enough room in your array, go ahead and set the element at this size to the new element. Right? Remember, this size is always one past as an index. It's always one past the last element in your array. Right? And of course, don't forget to increase the size of your list because you just added an element. If you go back and look at push for a stack, that's basically the exact same code. Okay, so in a list, most of the operations involve using an index. Right? You're going to remove by index. You're going to insert or add by index. You're going to get and set by index. So it's useful to implement a method that lets you check an index and throws an exception if needed. So my method check index is private because only the list is going to use this method. Right? You're going to check if the index is negative or if it's greater than or equal to the size. Right? In either case, you're going to throw an exception. Okay, so for get, all you have to do for get is go into the array at the specified index and return the element that's sitting there. Right? This is Java, so we should check the index to make sure it's valid because Java programmers are used to having checked access to stuff. Right? When you get the element out of the array, remember that the element type is actually big O object because our array is actually of type big O object. And so you have to cast the result back to E before you return it to the caller, because the caller is expecting to get back an element of type E. Set index is exactly the same as get. Right? You're going to set the element at that index to the incoming element. Set normally returns the element that was overwritten. So to get the element that was overwritten, we can call get. Right? So get gets the element at that index. It also checks the index for you. Right? So it validates the index for me, so I don't have to validate the index a second time in set. Right? Once I've gotten the value of the current element sitting at that index, I can simply overwrite that value with the new value elem, and then return the old value. Okay, add. So here's insert. This is the version of add that lets you insert at an index. Right. Notice the note at the bottom of the slide. Right. Okay, so the first thing we're going to do is we're going to check Is the index equal to the size? So remember, this version of add lets you insert at the end of the list. Right? The way you insert at the end of the list is you pass in an index equal to the size of the list. Right? Remember, the size of the list is not a valid index. So you don't want to check the index first. Right? The very first thing you want to do is check whether or not index is equal to size. Right? And if it is, that means I would like to add at the end of the list. So just call add, the other version of add. Right? And then, this is pretty important, immediately return from the method. Right? If you forget to return from the method and you do the rest of the method, you end up adding the element twice. Right? You add it once here, and then you're going to add it a second time down here. So that return statement turns out to be important. Right? Also, the other version of add increments the size of the list by 1 for us. So you don't want to increase the size of the list here by yourself. Right? Just let add do all of the work and then immediately return. All right, so once you've taken care of that special case, now you can check the index. Right? So you either add at the end or you add somewhere in the middle of the list. Somewhere in the middle of the list requires a valid index. So we should check that index first. Once we've done that, we now need to do the shuffle. Right? So for inserting into the list, you want to move everything to the right. So starting at, you want to move everything at the right. So move all the elements at the indexes, sorry. Oh, sorry again. You want to move all the elements starting at the element at index size -1, right? Then size -2, size -3, all the way down to index, right? You want to move those all one position to the right. Right? So you want to make sure your loop counts down from size -1. Okay. So my loop variable I starts as the size of the list -1. Right? The loop runs as long as I is greater than or equal to the index. The value of I decreases once each time through the loop. Right? You want to move the element from the right to the left. Okay. So the element from the right is the element at index I. Right? The element to the left of that is the element at index. Sorry, what am I doing? I plus 1. I'm moving them to the. Oh, sorry, I'm moving them to the right. Sorry, I'm being a dummy. All right, I want to start at the element at index I. The element to the right of that is at index I plus 1. Right. As soon as you write that, you're going to wonder. So first of all, you're going to check, right? So is this index I, is it always valid for this array? Right. The answer is yes, it's valid for the array. Right. I know that size -1 is a valid index for the array. Right? I know that index is a valid index for the array because I checked it up here. The question is I plus 1 a valid index for the array? Right. And so if you look at this thing, right, the largest value of I plus 1 is equal to the size of the list. And so the question is that a valid index for the array? The answer is, who thinks yes? Who thinks no? Okay, the no's have it. It is not always a valid index for the array, right? When is it not a valid index for the array? Right? It's not valid when your array is full, right? So if the number of elements in the list is equal to the capacity of the array, that's a problem, right? And that's what the bug is, right? If your array is full, what do you have to do? You have to increase the capacity of the array, right? And so what's missing is right here, right? Is the array full? Right? If the array if the array is full, you have to resize the array, right? Just like we did in that. So just like we did back here, right? So that part there is missing. Right? So remember, inserting into the list also increases the size of the list by 1. That means you have to make sure there's room in the array. Right? So that's the error that's on this slide. Okay, assuming you've resized the array, everything's fine. Right? Size plus the size is a valid index for the array, assuming you've got extra space in the array. Right? Now you go ahead and add the element at the index. right? So set the element at that index to the incoming element. Don't forget, increase the size of your list by 1. Right, and that's the implementation of add, which is really insert. Remove is similar, except you're going to move elements to the left and you don't have to worry about resizing. Right, so in remove, you don't worry about resizing because you're taking something out of the array. Right. So to remove an element, you would like to return the removed element back to the caller. So I'm going to call get to get that element. Right, calling get also checks the index for you. So that's nice. Right, I would now like to shuffle elements 1 position to the left. Right, so starting at index +1, right, I would like to move that 1 position to the left. Right, then I'd like to move the element index +2 1 position to the left, and so on and so on and so forth. Right, so starting at index +1, right, up to the last element in the list, right, shift that element 1 position to the left. Right. I know that's a valid index, right? I know that's a valid index. Sorry, I know I will always be valid, right? Because I is always less than this dot size, and it's never negative. Right? So I know I is valid, so I know that's not going to throw. Right? Might that throw? So that can only throw if I is 0. Then you get a negative index. Right? Can I be 0? The answer is no. I cannot be 0. Right? So this will never throw. Right? Can never be 0 because you always start at index +1, and the smallest value of index is 0. Right? All right. So once you've shuffled all the elements 1 position to the left, it's probably a good idea to take what was in the last position of the array and set that element to null. The reason you want to do this is if you don't do this, your array still has a reference to an object sitting in it, even though that object may no longer be required. Right? You're going to return that reference, that same reference back to the caller down here. Right? If the caller doesn't use the return value, then you can get rid of that object. Right? If you don't null the element in the array still has a reference to that object, and the virtual machine won't get rid of it. So it's probably a good idea to null the element. Right? Don't forget to decrease the size of the list by 1 because you just took something out, and then return the removed element. Right? And that's removed. So those are the basic operations that you're going to perform with that you're going to use when you're working with arrays. So when you're working with arrays, the thing either you're going to add at the end, you're going to remove at the end, you're going to add somewhere in the middle, or you're going to remove somewhere from the middle. Right? If you're removing from the middle, you're shifting elements to the left. If you're adding in the middle, you're shifting elements to the right. Okay, what about our iterator? So this is the last method in our class that we have to implement. So the way we're going to implement iterator is the same way that we implement, is similar to how we implemented an iterator, I guess, several weeks ago now. Right. So the way that we're going to implement this is that we're going to make our own little class inside of our list class. Right. So we're going to make a private class called ArrayIterator. Right. And it's going to implement the iterator interface. Right. Our iterator method simply makes a new object of type ArrayIterator and returns that back to the caller. Right. And so our ArrayIterator object needs to know how does it iterate over the sequence of the list, right, over the elements of our list. By making it a private, by making it an inner class, right? So remember, this is both nested and inner in Java. Those are Java terms. Right, so you have a class inside your array, inside your list class, right? So that makes it a nested class. The fact that it's not static makes it an inner class. Oops, sorry. I'm just going to. I just want to. Okay, I don't explain again what that means, right? So remember what an inner class lets you. Remember the properties of an inner class. Right? So if you have an inner class object. So if I have an ArrayIterator object, that object can only exist if there's also a list to iterate over. Right. So in other words, ArrayIterator can only exist if there is an S array list object. Right. Which makes it an inner class. Right. The inner class object has access to the outer class object. So every ArrayIterator object has access to the size field of its list and it has access to the array belonging to its list. Right? If this class was static, both of those things are not true. Right? So in a static nested class, right, the nested class does not have access to the fields of its enclosing class, and it can exist in isolation or without having an object of the outer class. Okay, so how does this thing work? So just to quickly review what actually is in the iterator interface, right? So remember what an iterator is, right? It's just an object. It knows how to iterate over the collection of elements, right? So our array iterator object, is that what I'm calling it? Yes, our array iterator object knows how to iterate over the elements in our array. One use of iterator is that it lets you write a for each loop for your class, right? So by providing an iterator for our list class, someone can now write a for each loop, right? So for each string s in our list t, do something with the string s. The way that the Java language actually lets you do that is it makes an array iterator object and hides all of the calls to the iterator object for you. The other important reason for creating an iterator is that it's the only safe way of being able to visit the elements in a list or set and then remove elements while you're looking at them, right? So you imagine writing a loop over the elements of a list, right? You look at the element and you decide you'd like to remove it from the list, right? If you just call remove if you call the lists remove method, there's a good chance that bad things will happen. Right. So in other words, either you'll miss removing something from the list, or you'll end up throwing an exception of some kind. If you want to iterate and remove at the same time, you need to use an iterator object. So remember what's in the interface. There's a hasNext method. Right. HasNext is true if there's still elements left in the sequence to visit. Next returns the current element that the iterator is looking at and then moves the iterator to the next element. We didn't implement remove before, but now we're going to implement remove. So remove lets you remove the last element that was returned by next. Right. So the way you use an iterator is you call next to look at the, you start out at the beginning of the sequence, you call next to get the first element of the sequence. If you'd like to remove it, you can then call remove. Right. Once you call remove, you have to call next again. So you're not allowed to call remove twice in a row, right? Or more than once in a row. So the remove method removes the element that was most recently returned by next. You're only allowed to call it once for each call to next, right? If you call it more than once for each call to next, you end up getting what's called an illegal state exception. Right. You also get an illegal state exception if you try to call next without calling remove. Right. So if you start out with an iterator at the beginning of your list and then you call remove right away, you also get an exception. This is how you iterate over the elements of a list or set and remove elements as you go. Right. So this is the only safe way to do it. You make an iterator object. So this is a list or set of integer. So you make an iterator over the elements of your collection, right? You make the iterator by calling your collection's iterator method. Each time through the loop runs as long as hasNext returns true, right? So as long as there's another element to visit, run the loop. There's no update condition here, right? Instead, the update happens inside the loop, right? So inside the loop, the very first thing you do is you call next, right? Next returns the element that the iterator is currently looking at, right? And then advances the iterator. So the fact that it advances the iterator takes the place of the update statement here. So here, I'd like to look at the value, right? If the value is less than 0, it looks like I'm removing all the negative values from this list, right? If the value is less than 0, you can use the iterator's remove method to remove the element. What you don't want to do is you don't want to use the lists remove method here, or the sets remove method here. Right? If you write t.remove, because t is our list or set, right? This is not guaranteed to work. Right? If you're using a list, what normally happens is you end up missing elements to remove. And if you do it too many times, you eventually end up with an exception of some kind. And if you do it with a set, same thing can happen. You either end up missing elements to remove, or you end up with an exception of some kind. Okay, so how do we implement this iterator? So it's a little bit different than how we did it previously. So an iterator for a sequence, you can imagine it as a cursor in your favorite word processor or text editor. Right. So here I've got a blinking cursor. This is from captured from Eclipse. Right there, my cursor is sitting between the Y and the I. Right. And so an iterator you can think of as sitting between elements. Right. So here my iterator is shown in red. Right. It's sitting between the elements at index 7 and 8. Right. So it's sitting between the 13 and the 16. If you call next with this iterator, right, it returns the 6. Right. So this iterator is currently looking at the element right in front of it. Right. So it'll return the 6, and then the iterator will shift one position to the right so that it's now between the 6 and the 10. So it looks like that after calling next. So return the 6 and then move one position to the right. Okay. At the end of the list, so this list has 15 elements in it. Right. So at the end of the list, has next returns false. If you call next, sorry, when has next is false, then you end up with an exception. Right. So here, this iterator has no more elements to look at in the list. Right. Calling next on that iterator causes an exception, indicating that there you've tried to look at a non-existent element. When you make a brand new iterator, it normally starts at the beginning of the list. Right. So at the beginning of the list, right, it sits right in front of the first element of the list. Right. Now, when we implement this iterator, the way we're going to do it is we're going to keep track of these two values, previous and next. So previous is the index of the element immediately in front of the iterator. Next is the index of the element immediately after the iterator. Right. So here, next will be 0, and previous, we're going to use -1 in this case. All right, so inside our sArrayList class, we have our array iterator class. Right, it implements the iterator interface, so it has to provide has next, and we're going to provide remove as well. Oh, I guess this is where I told you what this thing was. Right, so this is a nested inner class. Right, remember, an inner class has access to the members of its enclosing class. Right, so array iterator has access to the fields and methods of sArrayList. It adds its own fields, so it adds a field next and previous. Right, so notice the comments here. Right, so next is the index of the element returned by the next call to next. Right. Previous is going to be the element of the index returned by the most recent call to next. Right, so in other words, it's the index of the element that was returned the last time you called next. Right, we're going to reset that value to -1 if we remove an element from the list using remove. Right, and so that's how we're going to detect whether or not we've tried to remove. We tried to call remove more than once for a given call to next. Making a brand new array iterator object starts the array iterator at the beginning of the sequence. Right. So we want to set previous to 0, and we want to set next to 0. We want to set previous to -1. Right. So there's next and previous. Has next is easy to implement. Right. So remember, next is the index of the element returned by the next call to next. Right. So if you reach the end of the list, right? So if you reach the end of the list, then next will be equal to the size of the list. Right. So has next can return true, right? As long as next is less than the size of the enclosing array list. Right. Now remember, the syntax to get to the fields of sArrayList is weird. Right. You put the name of the enclosing class. So that's sArrayList. Then you put .this, and then you put the name of the field. Syntax is weird. That's just the way it works in Java. Right. But all that's saying is that as long as this next is less than the size of the list, there's something to look at in the list. Oh, wait, what does next do? So remember, next returns the element that next is pointing at, right? And then it advances the iterator one position to the right. Right. So I want to get the element that next is pointing at, or the index for which next is, right? So I can call get to do that. It's actually slightly inefficient to do it this way because get checks the index, and I know for a fact that the index is already valid. So you should probably do it this way, right? Go into the array, right? Get the element at this dot next, right? And return that at the end. Again, to get to either call the method belonging to the list, right? Again, you have to write this wacky, this strange syntax here, right? Again, the get method belongs to the array list, so you have to write sArrayList.this, and then you can call get that. Right. Similarly, if you wanted to go into the array directly, the array belongs to the array list, so you have to write sArrayList.this.arr. Once you've got the elements to return, advance the iterator. Sorry, here, advance the iterator to the next position. Right. So I'm going to increase next by 1. Right. Now notice for previous, I don't write this previous plus plus. Instead, I write this previous equals this next. Right. And you'll see why we do that in a second. Right. For next, you can just add 1 to next. Right. But that doesn't work for previous because of the way that we're about to use previous. Okay, so how do you remove stuff from a list using an iterator? So here's my iterator. It's sitting between the 6 and the 10. Right. The most recent call to next returned 6, right? The element sitting at previous. Right. If I call remove with the iterator, it's going to remove the 6. Right. So that's the way that iterators work in Java. Right. It removes the element that was last returned by next. So it should remove the 6. Now, if I remove the 6 from this list, right, the 10, the 4, the 14, and so on, they all have to move 1 position to the left. Right. Furthermore, right, if I call next with this iterator, I'm supposed to return the 10. Right. But watch what happens when you remove the 6. Right. So I have the iterator. I use the iterator to remove the element. Right. Notice that after removing the element, the 10 is now sitting here. Right. And that's the element that I'm supposed to return next. And so the iterator is now in the wrong position. Right. So calling remove removes the 6. Right. So what does that mean? I'm going to remove the element that's sitting at previous. It now looks like this. Right. Now, if I don't do something to the iterator and I call next, it's going to return the 4 and not the 10. So that's not good. Right. We have to adjust the iterator. Right. How do you adjust the iterator? You just subtract 1 from next. Right. So you subtract 1 from next. And so now next is pointing at the element at index 8, which is the 10. Right. So that's correct. So you can now imagine that the iterator has moved backwards 1 position. Right. Also notice that previous and next, they're now pointing at the exact same element. Right. So you might think that, well, we should just adjust previous by -1 and make it point at the 7. Right. But the way that the iterator is defined in Java is it says that the iterator interface says you cannot call remove more than once for each call to next. Right. And so the way that we're going to indicate that we've already called remove once is that we're going to set previous to -1 instead. Right. So in other words, we're not going to subtract 1 from previous to back the iterator up. We're going to set it to -1, and that lets us remember we've already called remove once. You can't call it again until you call next. Right. And so when you call next, right, you end up resetting previous to a non-1 value. Right. So that's why I wrote this previous equals to this next here instead of adding 1 to previous. Right. If we're going to set previous to -1, adding 1 sets it back to 0, and now your iterator is messed up. So to remove, first thing we're going to do is we're going to look at the value of previous. Right. If it's -1, then either the iterator is at the front of the list and there's nothing to remove, right, because you haven't called next yet, or you've already called next. Right. sorry, you've already called remove and you haven't called next again. Right? So if previous is equal to -1, throw an exception. Right? Otherwise, you can remove the element sitting at this dot previous. Right? How are you going to remove that element? Well, list has got a remove method, so we might as well just use that. Right? So ask the list to remove that element. Right? Once you remove the element, we have to back the iterator up one position. Right? So we move, we set next, we subtract 1 from next. Right? And then we remember, hey, we've called remove already. Right? We better not call it again. So we set this previous to -1. And there's your iterator.